On December 9th, 2024, a team of physicists at Google published a result that ran directly against nearly 30 years of expectation in their own field. For as long as quantum computers had existed as a serious engineering pursuit, adding more of the fragile quantum bits that make them work had always made things worse. More qubits meant more opportunities for errors to creep in, more noise, more instability, a problem that had haunted the entire field since its earliest theoretical papers in the 1990s. Google's team showed the opposite happening on their own hardware. A system where adding more qubits made the errors go down, not up, and kept doing so reliably, exponentially, every single time they scaled the system further. One of the researchers behind the result described watching it happen as something the entire community could finally breathe a sigh of relief over. This is the story of Willow, Google's quantum processor, and the specific, carefully documented moment when quantum error correction, a problem the field had been chasing since before most of the researchers working on it today were born, finally started behaving the way theory had always promised it should, along with what's happened on that same chip in the 2 years since, as Google has continued pushing it toward genuinely useful, real-world applications. To understand why this particular finding mattered so much, you first need to understand exactly what problem quantum error correction was actually trying to solve, why it proved so stubbornly difficult, and why nearly 3 decades of dedicated research hadn't managed to fully crack it before Willow came along. Quantum computers promise genuine advantages over classical computers for certain kinds of problems, ranging from simulating complex chemical reactions, to modeling new materials, to potentially breaking certain kinds of cryptographic codes, precisely because they exploit quantum mechanical properties, superposition and entanglement among them, that classical bits simply can't replicate. A classical bit can only be a 0 or a 1. A qubit can exist in a combination of both states simultaneously, and multiple qubits can become entangled with one another in ways that allow a quantum computer, in principle, to explore an enormous number of possible solutions to certain problems all at once, rather than checking them one at a time, the way a classical computer must. But that same quantum behavior comes with a serious, well-known cost. Qubits are extraordinarily fragile, prone to losing their delicate quantum state from even tiny amounts of noise, heat, stray electromagnetic interference, or simple interaction with their surrounding environment, a phenomenon physicists call decoherence. According to Google's own published research, even state-of-the-art quantum devices typically experience at least one failure in every 1,000 operations, an error rate far too high to reliably run the kind of long, complex calculations quantum computing's most promising applications actually require, calculations that can call for billions or even trillions of individual operations, to complete successfully without a single uncorrected mistake derailing the entire result. The theoretical solution to this problem has been understood, at least in rough outline, for nearly 30 years since the mid-1990s. Group many individual, error-prone physical qubits together into a single, more robust logical qubit, using a carefully designed mathematical structure called an error-correcting code, so that if any individual physical qubit within that group experiences an error, the system as a whole can detect and correct it without losing the overall quantum information being stored. In principle, adding more physical qubits to each logical qubit should make that logical qubit increasingly resistant to errors, since there's more built-in redundancy and more opportunity for the surrounding system to catch and fix any single mistake before it corrupts the entire calculation. In practice, for nearly 3 decades, this simply didn't work the way theory suggested it should. Adding more physical qubits to a code typically introduced more opportunities for something to go wrong, faster than the code's own error-correcting structure could actually keep up with, meaning larger, more elaborate error correction codes often performed worse in practice than smaller, simpler ones, exactly the opposite of what researchers actually needed if they ever hoped to build a large-scale, genuinely reliable quantum computer capable of running real, useful programs. Overcoming that specific obstacle, crossing what researchers in the field call the error correction threshold, the precise point where adding more qubits finally starts helping, rather than hurting overall system reliability, had become one of the most closely watched, most consequential open problems in the entire discipline, discussed and pursued across dozens of competing research groups and multiple entirely different physical approaches to building a working qubit in the first place. That's exactly the threshold Google's team crossed with their Willow processor, and the way they demonstrated it involved a carefully staged, deliberately escalating experiment, built specifically to show the pattern unfolding step by step, rather than simply announcing a single, isolated result. According to the research, published in the prestigious journal Nature under the direct title Quantum Error Correction Below the Surface Code Threshold, the team built logical qubits out of increasingly large grids of physical qubits, arranged as square lattices measuring 3 by 3, then 5 by 5, then 7 by 7, each larger grid representing a genuinely more ambitious version of the same underlying error-correcting code. Each time the team increased the size of that lattice, the resulting logical qubit's error rate dropped by roughly half, a clean, repeatable, exponential pattern rather than a one-off improvement. Michael Newman, a research scientist on the Google Quantum AI team, described the milestone directly and simply: "We are finally below the threshold." Hartmut Nevin, the founder and lead of Google Quantum AI, put the achievement in blunter, more personal terms in comments given afterward, describing how the team went from a code distance of 3 to 5 to 7, halving the error rate each time in what he called an exponential reduction of error rate, adding that he felt the whole community could finally breathe a sigh of relief because it demonstrated conclusively that quantum error correction really could work in practice, not merely as a promising idea confined to theoretical papers and computer simulations. That specific pattern, error rates dropping by roughly half with each successive increase in qubit count, is exactly the signature scientists had been chasing since the theoretical foundations of quantum error correction were first laid out decades earlier. It meant that, at least for this specific class of error-correcting code, called a surface code, Willow's logical qubits genuinely did get more reliable as they got larger rather than less reliable, a qualitative shift researchers described using the term beyond break-even, meaning the resulting logical qubit actually lived longer, remained coherent and stable for a longer stretch of time than any of the individual physical qubits used to construct it. As Google's own research blog put it directly, this represented, in their words, an unfakeable sign that error correction really was improving the overall system, rather than simply adding complexity and overhead without delivering any genuine measurable payoff in return. It's worth being fair and precise about how this particular result sits within the broader competitive landscape of quantum computing research, rather than treating it as though Google achieved something no other research group anywhere had ever come close to approaching. As science journalism coverage of the finding in the peer-reviewed journal Science pointed out at the time, researchers working with entirely different physical implementations of qubits had also been closing in on broadly similar milestones around roughly the same period. A team at Harvard University, using individual trapped atoms suspended in place as their qubits rather than Google's superconducting circuits, had already shown back in December of 2023 that they could reduce a logical qubit's error rate by encoding that same logical qubit across increasingly large grids of atoms, a conceptually similar approach applied to a very different underlying hardware platform. A separate team at Yale University had demonstrated its own independent version of beyond threshold error correction even earlier, back in 2022, using yet another entirely different physical approach, encoding qubits not as superconducting circuits or individual atoms, but as specific modes of microwave radiation trapped and sustained inside a hollow aluminum cylinder. Google's specific contribution, according to Caltech theoretical physicist John Preskill, a widely respected figure in the field who has closely tracked this competitive landscape for years, involved something genuinely novel layered directly on top of those earlier, independently achieved results from Harvard and Yale. The Google team, Preskill noted, managed to decode the auxiliary qubits used throughout the error correction process repeatedly, on the fly, continuously, in real time as the computation was actually running. A capability he described as essential for genuinely using logical qubits to perform useful computation going forward, rather than simply demonstrating, as an isolated experiment, that a logical qubit could remain stable while sitting largely idle, disconnected from any actual ongoing calculation. Alongside the error correction milestone itself, Google's team also used the same Willow chip to run a specific, separate benchmark task called random circuit sampling, a computation deliberately chosen by the field specifically because it's considered essentially impossible for any classical supercomputer to complete within any reasonable amount of time, making it a widely used, if somewhat abstract and practically limited, test of a quantum processor's raw computational speed relative to classical alternatives. According to Google's own published account of the work, Willow completed that specific benchmark task in under 5 minutes of actual runtime. The company estimated that reproducing the exact same calculation using one of the world's most powerful existing classical supercomputers would take roughly 10 septillion years to finish, a number so almost incomprehensibly large that it exceeds the current best scientific estimate of the entire universe's own age by many, many orders of magnitude. Google's CEO, Sundar Pichai, highlighted that specific comparison directly and publicly, framing Willow as an important concrete step toward eventually building a genuinely useful quantum computer, one capable of tackling practical applications in fields, including drug discovery, fusion energy research, and next-generation battery design. It's worth being honest, in that same breath, about exactly what this particular benchmark result does and doesn't actually demonstrate, since drawing that careful distinction is part of what separates an accurate, trustworthy account of this technology from an overstated, misleading one. Random circuit sampling, the same general category of benchmark task Google had previously used back in its original 2019 quantum supremacy announcement involving an earlier chip called Sycamore, doesn't have any direct practical real-world application on its own, and researchers involved in the field have always been fairly candid about that limitation. It's specifically chosen as a benchmark precisely because it's mathematically difficult, essentially intractable, for classical computers to simulate accurately, making it a genuinely useful stress test of raw quantum processing speed under controlled conditions. But completing it successfully doesn't by itself prove that a quantum computer can reliably solve the kinds of problems people actually care about in the real world, like designing new pharmaceutical compounds or accurately modeling new battery chemistries from first principles. That important distinction is exactly why Google's subsequent work on that same underlying Willow hardware, extending well beyond this initial error correction and raw speed demonstration, matters so much for understanding where this technology has genuinely progressed to since. In October of 2025, building directly on that same underlying Willow architecture, Google's team introduced a new algorithm called quantum echoes, designed specifically to close the gap between raw computational speed on one hand and genuine independently checkable usefulness on the other. Unlike random circuit sampling, quantum echoes produces a result that corresponds to something with real, direct physical meaning, a specific kind of measurement called an out-of-time order correlator, which describes precisely how a small disturbance introduced into a complex quantum system spreads, scrambles, and interacts across that entire system over time. Because that particular measurement corresponds to something physically real and independently meaningful, rather than an essentially arbitrary output pattern with no external point of comparison, it can actually be checked and verified through separate, entirely independent means, including by comparing the quantum computer's own results directly against real physical laboratory measurements taken using long-established conventional chemistry techniques. Running on the Willow chip, using as many as 105 individual qubits, quantum echoes completed its core calculation roughly 13,000 times faster than the best currently available classical algorithm running on one of the world's most capable existing supercomputers, according to Google's own detailed published account of the work. Crucially, and unlike the earlier 2019 supremacy demonstration involving Sycamore, this particular result was genuinely reproducible and independently verifiable by outside researchers, marking, according to Google's own careful framing of the achievement, the first verifiable quantum advantage in the entire history of computing, a meaningfully different and more scientifically significant claim than simply being fast. Working directly in partnership with researchers at the University of California, Berkeley, the Google team applied the same quantum echoes algorithm to two real physical organic molecules, containing 15 and 28 atoms respectively, and found that the quantum-derived structural results not only matched existing laboratory measurements gathered through traditional nuclear magnetic resonance techniques, but in certain specific cases actually revealed additional fine structural detail that conventional NMR methods alone genuinely struggle to extract cleanly on their own, offering a real, tangible, near-term glimpse of how this kind of quantum computing capability might eventually meaningfully assist with genuine practical problems in drug discovery and materials science research. The most recent chapter in this ongoing story, as of the middle of 2026, involves something considerably less flashy and headline-grabbing than a dramatic new speed record, but arguably just as important for the field's genuine, sustained, long-term progress. In research published in the journal Nature in July of 2026, a Google-led research team demonstrated a quantum computer capable of actively learning from its own accumulated errors while it continues running an ongoing computation, rather than relying entirely on a fixed set of error correction parameters that had simply been carefully calibrated in advance by human researchers and then left largely unchanged throughout the entire operation. The system uses a reinforcement learning approach, a well-established artificial intelligence technique, in which a system gradually improves its own behavior over time based directly on feedback drawn from its own recent performance. Applied here directly to the continuous stream of error correction data Willow already naturally generates during ordinary, everyday operation. According to the published findings, this reinforcement learning-based approach reduced the processor's overall logical error rates by roughly 20%, beyond what conventional, carefully expert-tuned calibration alone had previously been able to achieve on the same hardware, and made the system's day-to-day performance 3.5 times more stable and consistent when researchers deliberately introduced artificial hardware drift into the experiment, meaning small, gradual, realistic changes in the physical behavior of the chip's individual components over time, precisely the kind of slow drift that any real, long-running quantum computer will inevitably experience naturally as its hardware ages and its immediate operating environment shifts in subtle ways. That specific advance genuinely matters because it directly addresses a practical, if considerably less headline-grabbing engineering problem, keeping a quantum computer performing reliably, not just during a single, carefully staged, one-time demonstration built specifically for a press release, but continuously, over extended, sustained stretches of real operation, as its physical components naturally drift and change in small, cumulative ways over time. A future, genuinely fault-tolerant quantum computer, the kind ultimately capable of running the sort of extended, complex, real-world calculations Google's own long-term roadmap explicitly aims for, will eventually need to operate largely autonomously for long periods without constant, hands-on, human recalibration, and this reinforcement learning approach represents a meaningful, concrete, practically demonstrated step directly toward exactly that kind of self-sustaining, adaptive, long-term reliability. Alongside that specific work, in January of 2026, Google's research team also published a separate paper describing what they call dynamic surface codes, a further evolution of the same basic error correction architecture originally used in the landmark 2024 below threshold demonstration, specifically designed to use fewer physical connections between individual qubits, remove certain particularly troublesome kinds of correlated errors that had proven genuinely difficult to address using the original static version of the surface code, and open a realistic path toward eventually implementing error correction using a hexagonal, rather than square arrangement of qubits on the chip itself, a meaningful geometric change that would allow each individual qubit to connect to only 3 neighboring qubits instead of 4, considerably simplifying the physical design, wiring, and overall fabrication process required for future, even larger scale quantum chips. According to Google's own account of this particular body of work, these specific demonstrations, taken together with a closely related achievement involving something the team calls color code operation running on that same underlying Willow architecture, firmly establish that quantum error correction genuinely can work using approaches that go well beyond just the original static surface code method alone, pushing the entire field noticeably closer to what Google describes as its next major internal milestone, achieving a long-lived logical qubit with a sustained error rate below 1 single failure per million. Individual cycles of error correction, a level of practical reliability that would represent a genuinely dramatic order of magnitude improvement over what's currently achievable using any existing quantum hardware anywhere in the world. Google has been notably explicit and refreshingly consistent publicly about how all of this individual incremental progress fits together into a considerably longer-term, publicly documented roadmap, one the company first laid out in detail back in 2020 and has continued tracking closely and transparently in the years since. Niven, reflecting candidly on the field's overall trajectory in a statement accompanying some of this more recent 2026 work, noted directly that the specific milestones the team has hit along the way are tracking remarkably closely with what was originally laid out on that same 2020 roadmap document, and that the next genuinely major milestone on that roadmap, a considerably larger, more capable machine the company refers to internally simply as Milestone 6, is currently expected to arrive sometime around the end of the current decade, assuming continued, steady progress at roughly the pace demonstrated so far. Kelly, Google's director of quantum hardware, offered a useful, appropriately grounded comparison for understanding exactly how Willow genuinely relates to the company's considerably earlier Sycamore chip. The same processor originally responsible for that first, more limited 2019 quantum supremacy claim, Willow, in his own straightforward description, represents essentially all of the good, genuinely valuable qualities that originally made Sycamore notable in the first place, but now paired with meaningfully better performing individual qubits, and considerably more of them working together as a coordinated whole. It's worth stepping back one final time and being fully direct about what all of this genuinely adds up to in practice without letting any single impressive-sounding number or comparison do more persuasive work than it honestly fairly deserves. Google hasn't built a quantum computer currently capable of solving ordinary, everyday problems meaningfully faster than existing classical computers already can, and nothing described here suggests that particular outcome is genuinely imminent in any immediate, near-term practical sense. What the company has actually concretely demonstrated across a carefully sequenced, multi-year series of peer-reviewed publications, each one building directly and logically on the one immediately before it, is a coherent, methodical, largely on schedule path toward exactly that eventual, longer-term goal. First, successfully crossing the long-sought error correction threshold that had genuinely eluded the entire field for nearly 3 consecutive decades. Then, going on to demonstrate a genuinely verifiable quantum computational advantage on a specific, physically meaningful calculation with real scientific value, rather than merely an Abstract, purely mathematical benchmark with no useful real-world point of comparison. And now, most recently, building precisely the kind of adaptive, self-correcting, continuously self-improving reliability that any eventual large-scale, genuinely useful quantum computer will unavoidably require in order to run continuously over genuinely extended periods of real-world operation without constant, ongoing human intervention and recalibration. None of that required any exaggeration whatsoever to be genuinely worth taking seriously on its own considerable merits. A team of dedicated physicists and engineers set out, quite deliberately, to solve one specific, extremely well-defined, and extraordinarily difficult technical problem, one that had actively resisted meaningful, sustained progress for close to 30 consecutive years. Finding a way to add more qubits to a working system without simultaneously making that same system meaningfully less reliable in the process. And they solved it carefully, methodically, transparently, with results published openly in a rigorously peer-reviewed scientific journal and subsequently confirmed independently by respected outside experts working across several entirely different, competing physical approaches to the exact same underlying scientific challenge. Everything that has followed since that original 2024 breakthrough, the genuinely verifiable quantum echoes result achieved in 2025, the reinforcement learning-based self-correction system demonstrated in 2026, the dynamic surface code architecture published earlier this same year represents that same dedicated research team continuing to build patiently, carefully, and incrementally on that original, genuinely hard-won scientific foundation. If you want to follow how Google's broader quantum computing roadmap continues to develop as the company works steadily toward its next major internal milestone, by the end of this decade, that research remains very much ongoing right now, with meaningful new results continuing to arrive roughly every few months as the underlying Willow architecture keeps getting pushed further. Subscribe if you'd like to keep following where it goes next.